Hello everybody, this is Dr. Bricker here with a Homework 2 help video. So the first problem is one point in space, the electrical potential energy, okay, so be careful, this is electrical potential energy, not electrical potential energy of a 20 nanocoulomb charge is 36 microjoules. What is the electrical potential at this point? In other words, what is the voltage at this point? You can tell from the units. Part B is, what if you were to put a 25 nanocoulomb charge at that point, what would the potential energy be? Okay, so we need to get the voltage from the first part to use it for the second part here. And just be careful, this is measured in microjoules. If you need to review this concept, click here and it'll take you to the correct section of the book. Okay, let's take a look at this one. Okay, so for this problem, we're given the charge, 20 nanocoulombs, so that means 20 times 10 to the minus 9. We're given the electrical potential energy in microjoules, so 36 to the minus 6 joules, and we want to know the voltage. So from this chapter, we know how the energy and the voltage are related to each other. So this is electrical potential energy. Sometimes this is just called electrical potential. Same thing as voltage. So we know that U is equal to Q times V. Notice there's no absolute value sign here with Q. Okay, so we know the energy and the charge. We want to do find the voltage. So energy divided by charge gives us the voltage then. Okay, so this will be joules per coulomb, which is a volt. It comes out in volts. Once you get this voltage for part B, you want to find the energy. So if you know the voltage, which you got from this part, and the charge of part B, you can figure out the energy. Okay, that's the use of voltage. If you know the voltage at a point in space and you try to put a charge there, you know how much energy will be stored there, or how much work you have to do. Okay, let's look at the next one. What potential difference is needed to accelerate helium plus ions, so that means a charge of plus E, or 1.6 to the minus 19th in other words, and a mass of 4 atomic mass units, so we'll have to look up what that is, from rest, so initial speed of 0 to a final speed of 1.8 times 10 to the 6th. So what kind of voltage do you need to accelerate a helium ion to that speed? All right, let's take a look at it. Okay, so I looked this up. One atomic mass unit, we used to call them AMUs when I was a kid, actually. Now they're just this simple U. 1.67 to the minus 27th kilograms. The charge they give you, it's 1.6 to the minus 19, so it must have lost an electron. We're going from an initial speed of 0, this is little v, that's for speed, to a final speed of 1.8 times 10 to the 6th. You might have different numbers, so be careful. What potential difference do we need for that to happen? So here's a charge at rest. If you put it here, it's going to go from some initial voltage to some final voltage. This physically is a way that you could do it. It doesn't say there's a capacitor. I'm just giving you a scenario where you could actually get this to speed up, being repulsed by the positive side, attracted by the negative side. So really, if you look at this, we're going to be accelerating from this side over to this side. So the final voltage over here is going to be lower than the initial voltage, right? Because we're going downhill. That's how it works. You go from a higher potential to a lower potential. So if you wanted to figure out the potential difference, this would be kind of going from a lower side to a higher side. So this could be something like 0 and 10. So the potential difference would be where you end up, 0 minus where you begin, 10. So technically the potential difference in this problem is negative. Okay? We'll see if that actually happens when we put our numbers in. Okay, so here's the formula. The change in kinetic energy is equal to minus the change in electrical potential energy. And from this chapter, we know the change in electrical potential energy is Q times delta V. So that this minus sign is in the formula. This minus sign is from the formula. Okay, so the change in kinetic energy is 1/2 mv final squared. This is the velocity here, squared. That's what kinetic energy is. Minus 0, because we're starting from rest, equal to minus q times delta V. So divide both sides by minus Q then to get delta V. And you see that it actually will come out to be negative then. So what do you use for the mass? Well, it's 4 atomic mass units, so 4 times 1.67. The final speed's given in the problem. The charge is also given. So this is going to come out to be negative, which it physically should. Okay? All right, let's look at the next one. So the Cassini spacecraft that visited Saturn and its moons did more than take pretty pictures. It also returned physical data. Saturn's moon Titan, that's shown in the picture, has a substantial atmosphere, and Cassini went through to detect atoms and molecules from the atmosphere. It measured the atmospheric composition with a time-of-flight mass spectrometer. These are used all over the world right now, actually. And good. Ionized atoms and molecules were accelerated through 30,000 volt potential difference, so 30,000 volts, and sent through a chamber of length 18.8 centimeters. The time to travel the length of the chamber was measured, with heavier particles taking longer. What is the time of flight for a singly ionized molecule of water? So water enters, singly ionized, again, means it has a charge of, depending on what it is, plus or minus 1.6 to the minus 19th coulombs. So this water molecule went in through this voltage and was accelerated. We can figure out how fast it's going after it goes through that potential difference. And then knowing how fast it's going, and knowing that it has to go through a distance then of 18.8 centimeters, we could figure out how long that takes. So similar to the previous problem, just a little bit more to it than that. Just this little added time part. All right, let's take a look at it. Okay, so first let me draw your attention to this picture here. How could you actually get an ion to accelerate? So if this were a capacitor, positive plate, negative plate, a positive charge would go flying across this way. So when that happens, we're going from a higher potential to a lower potential. For example, if this were 10 and this were 0, a positive charge would accelerate across. So in that case, the potential difference is actually negative. I'm just going to give you a pretend situation, 0 and 10 volts. That's not what we have here, but I'm just saying if it's 10 and 0, the potential difference from this side to this side would be where you end up 0 minus 10. So technically, if this were a positive ion, the potential difference to accelerate it would be negative 10. On the other hand, if this were a negative charge going this way, the potential difference would be positive for this negative ion. Right? The charge would be negative, potential difference would be positive. Here we have a positive charge, the potential difference is negative for it to fly across. So in this problem, let me just assume that the charge is positive, and then the magnitude of the potential difference was 30,000 volts. Really, for a positive charge to accelerate across, we've got to have negative 30 times 10 to the third. And I'm assuming that it's, well, they tell you actually, the charge is 1.6 to the minus 19th. I'm just assuming it's a positively charged water molecule. So if we could figure out how fast we're going, this is the speed, after going through this potential difference, figure out how fast we're going, then we could figure out how long it takes to get across. Remember, the speed is the distance over the time, so the time is the distance divided by the speed. Okay, so first let's figure out how fast we're going. This is velocity. And then after knowing how fast we're going, we can figure out how long that takes. Okay, so change in kinetic energy is minus the change in potential energy. We saw that in the previous problem. Minus Q times delta V. Okay, so the change in kinetic energy, final kinetic energy, 1/2 mv squared, minus the initial, we're assuming we're starting from rest, minus Q times delta V. So you'll have to do a few steps of algebra to get the final speed here. So what is the mass? Well, it's a hydrogen molecule, so you'll have to figure out the mass of hydrogen in kilograms. So you got 2 hydrogen, 1 oxygen, figure out the mass that you have in kilograms of an H2O molecule. And then be careful, there's a minus sign in the formula, but also you have to use negative 30 kilovolts. That's for the first part. They don't actually ask for how fast you're going, but you need to get how fast you're going to to actually answer the question that's being asked. And then you can use this to figure out how long it takes to get across. 18.8 centimeters is 0.188 meters. So divide by 100 when you go from centimeters to meters. Okay, let's look at the next one. In proton beam therapy, a high-energy beam of protons is fired at a tumor. The protons come to rest in the tumor, depositing their kinetic energy and breaking apart the tumor's DNA, thus killing its cells. For one patient, it's desired that 0.1 joules of proton energy be deposited in a tumor. To create a proton beam, protons are accelerated from rest, so initial speed of 0, through 22 megavolts, so 22 times 10 to the 6th volts. Good. So this is excellent. You don't have to actually, do surgery. Maybe you have somebody has a brain tumor. You don't have to get into their actual skull and try to remove the tumor that way. Here we're having a directed beam of protons going right to the tumor and depositing all the energy in the tumor, almost like magic. What is the total charge of protons that must be fired in nanocoulombs? Okay, so here's the total energy. Here's the voltage. We could figure out the total charge associated with that. This one we don't actually have to figure out how fast each proton's going or how many protons, although we could if given a little bit more information. Here we just want to know the total charge associated with 0.1 joules of proton energy going through 22 megavolts. Let's take a look at it. So again, we've got 0.1 joules, delta V of 22 times 10 to the 6th volts. We can figure out the amount of charge from really the first formula that we saw in this chapter. Delta U is equal to Q times delta V. We're given the amount of energy, that's the 0.1 joules. We're given the voltage difference, 22 megavolts, so 22 times 10 to the 6th volts. So delta U over delta V will give us the charge. And then make sure you put it into nanocoulombs. Okay, on to the next one. So this one we have two 2.5 centimeter by 2.5 centimeter plates that form a parallel plate capacitor. Okay, so we can use this to get the area of the plate. Just be careful, we got to put it in meters. Charged to plus or minus 0.708 nanocoulombs. So one plate has plus 0.708 nanocoulombs, the other negative 0.708 nanocoulombs. What is the electric field strength inside the capacitor? So the electric field strength, this really goes back to the previous chapter. If the spacing between them is 1.2 millimeters, and then part B, what is the voltage, or in other words, potential difference across the capacitor? This really is from this chapter. Let's see what C and D call for. Electric field if the separation is 2.4 millimeters. Okay, so similar problem with C and D. So let's take a look at A and B. Okay, so each plate is 2.5 centimeters by 2.5 centimeters. The charge here is on each plate 0.708 to the minus ninth. One is positive, one is negative. The separation is 1.2 millimeters. We need that to be in meters, so 1.2 millimeters times 10 to the minus third. And here's a constant that we're going to need for this problem, epsilon naught. So this goes back to the previous chapter. The electric field strength is the charge divided by epsilon naught times A. Okay, so we can do that. We did that in the previous chapter. Then to get the voltage across the capacitor, it's E times D. Okay? So electric field strength then is the charge. It's just the charge, the magnitude of the charge on one of the plates. So 0.708 to the minus ninth coulombs. We do this so it makes it a little more clear. That's the charge. Divided by epsilon naught, which is 8.85 to the minus 12 coulomb squared per Newton meter squared. That's where the Newton meter squared is coming from. I put it in the numerator because it was way down here. And then also we've got the area. So 2.5 centimeters, 0.025 meters, and it's square, so we need the area, you got to square that. So put that all together. You see, as far as the units go, the meters squared cancels out. One of the coulombs cancels out, and we're left with newtons per coulomb. Be careful, you might have different numbers than I have. And a newton per coulomb, as you saw from the chapter 21 notes, or actually I guess it would be chapter 20 notes, a newton per coulomb is the same thing as a volt per meter. That's the electric field strength. Now if you make the plate separation larger, the electric field doesn't change. There's no plate separation in this formula. Just keep that in mind when you do part C. Don't be surprised if you get the same number. But you will, because there's the plate separation is not in this formula here. And then the voltage across the capacitor is E times D. So we got this from the first part. The separation 1.2 millimeters, or 1.2 to the minus third meters. And then you see the meters cancel out, and we're left with volts. That's one reason I wrote it as volts per meter, so you could see how the units work out. Okay, good. So voltage across the capacitor. Let's take a look at the next one. Okay, so here's a point charge, 2 nanocoulombs. We want to know what's the potential difference, V, delta V from A to B, which is the voltage at B here minus the voltage at A, which is here. Now, if you notice, this is a point charge. The formula for the voltage due to a point charge is KQ divided by R, where R is the distance away. So point A and point B are the same distance from this point charge, so the voltage at B and the voltage at A are the same thing, so there is no potential difference. This is an equipotential surface here. So the answer to the first part is 0. There is no potential difference. You're at the same height if you use the topographical map analogy. What's the potential difference between VC minus VB? Okay, so C is over here, 2 centimeters away. B is here, 1 centimeter away. They're not at the same potential. They're at different potentials. So we want to do VC minus VB. So don't be surprised if you get a negative answer for this one. You'll have to put your numbers in and see what you get. Let's take a look at it. Okay, so for a point charge, the voltage due to a point charge is KQ divided by R, where R is the distance away. So the potential difference at C minus the potential difference at B, that's what they're asking for. This would be the voltage at C, so KQ divided by the distance to C. That's the distance to C. Minus the voltage at B, which would be minus KQ, and then the distance to point B. That's this distance. That's not as far. Okay, so put all the numbers together there. K is the constant that you've seen before. Just to remind you, 9 times 10 to the 9th newtons meters squared over coulomb squared. That's a squared, believe it or not. Okay, not too bad. So just for a point charge, you have a potential difference around a point charge. Let's look at the next one. Okay, so here we have 3 point charges. One here, here, and here. And we want to know the electrical potential, or in other words, voltage, you can tell by the units, at this dot down here. So pretend that the upper left and the upper right are not there. You could figure out the potential here just because of this one. We just did a similar problem on the previous one. You know, use KQ divided by, and this is the Q I'm talking about, KQ divided by 0.03 meters to figure out the voltage at this spot because of this one. Now pretend lower left and upper right don't exist. Figure out the potential at the dot because of the upper left one, KQ divided by this distance. And you can get that distance. This is a 3, 4, 5 triangle. So there's a contribution here from the upper left one, which would be KQ, and here's the Q. It turns out that they're all the same charge. Divided by this distance, so 0.05 meters. And then there's a contribution at the dot from the upper right one. This distance is 4 centimeters. So you'll have 3 terms, KQ divided by this distance plus KQ divided by this distance plus KQ divided by this distance. The Q's are all the same. Okay, so I'm not going to write that one down. Again, you can review the concept here. Next one. Determine the magnitude of the electric field at point 1. There's point 1. and the direction of the electric field at that point. And then part C, determine the magnitude of the electric field at point 2 and the direction at point 2. And point 2 is down here. Okay, let's do part A and B, and then I'll leave C and D for you. Part B is actually, we'll do part B first. Determine the direction of the electric field at the point. Okay, so the electric field goes from higher to lower potential. This is a 50 volt equipotential surface. This is a 25 volt equipotential surface. So we're going to be pointing down the hill. We're going to be going this way from 50 to 25, so downward. Now to get the magnitude of the electric field, so remember the potential difference is equal to E times D, or maybe I should say E times X. So from that idea we can figure out the magnitude of the electric field here at point 1. Let's put that one on paper. Okay, so here's the formula. Delta V is equal to E times X. So E would be delta V divided by X. This comes from chapter 21 again. Now, looking at point 1, above point 1 we had 75 volts. Below point 1 we have the line with 25 volts. So the potential difference around point 1 would be 75 minus 25, you know, the line above it, the line below it. And then that distance is 2 squares worth. Each square is 2 centimeters if you look at the key there on the picture. So the distance would be 0.04 meters, and you can get the electric field. That's how the electric field and the potential difference are related to each other. And then you can do a similar thing for part C and part D. See, we're going above it is 75, below it is 25. That's why I did 75 minus 25, and then divided by this distance from the 75 line to the 25 line. And each square is 2 centimeters. Okay. Next one. Nerve cells in the body can be electrically stimulated. A large enough change in the membrane potential, so the voltage in other words, triggers a nerve impulse. Certain plants work this way, so-called sensitive plant. So a touch to a sensitive plant causes the leaflets to fold inward and droop. We can trigger this response electrically as well. You kind of like hooking the plant up to an electrode. You provide the voltage and you can get the plant to twitch. So in one experiment, investigators placed electrodes on the thick tissue at the base of the leaf. Electrodes were 3.5 millimeters apart. When the electrodes were connected to 47 microfarads, okay, so remember farads are the units of capacitance. So that's the capacitance there. And here's the voltage it's charged to. This stimulated a response from the plant. Eventually, all the charge of the capacitor was transferred to the plant. How much charge was transferred? So if you've got this much voltage on this sort of capacitor, how much charge does that correspond to? And then the second part is, what is the electric field between the electrodes? Okay, very good. So let's take a look at it actually. Part B is similar to what we just did. So if you've got this much voltage, 1.5 volts, actually let's just talk our way through B. We've got this much voltage over a distance of 3.5 times 10 to the minus third meters. What's the electric field? So from the previous problem we saw that the electric field was delta V divided by the distance between the plates. So if you take 1.5 volts divided by 3.5 to the minus third meters, you'll get the electric field strength. Okay, so let's take a look at this in a little more detail. Okay, so for capacitors, you know that the charge is proportional to the voltage across the capacitor. To make this into an equality, we need some constant of proportionality here. So Q is equal to C times delta V. So the constant of proportionality between charge on a capacitor and the voltage across the capacitor is called the capacitance. And it just comes from what the capacitor, the plate separation and the distance between the capacitor. So in this problem, we're given the voltage across the capacitor. we're given this constant of proportionality, 47 microfarads, so it's 47 to the minus 6 farads, and I put off to the side. Don't forget, a farad is a coulomb per volt. So if you know the voltage across and the capacitance, how much charge do we have? Okay, so we're starting to get into more abstract ideas here. I mean, what is a farad in your life, you know? Well, it's a measurement of capacitance, but it's less tangible than, say, a meter or a second or a kilogram. We know what those are. A farad is more abstract. So it's a good idea to know what these units are in terms of other units, and then that could be helpful. So a farad, again, is a coulomb per volt. So in the formula, this is capacitance times voltage. So farad, okay, again, what is a farad? Coulomb divided by volt, multiply it by a volt, and we end up with coulomb. So whatever this turns out to be, this is the amount of charge that the leaf was deposited into the leaf. And then the second part, what's the electric field? This is the part I was saying, this is just like the previous problem. Delta V is equal to E times X. So E is delta V over X. The voltage is given, 1.5. The distance between the electrodes is also given, 3.5 millimeters, so it's 3.5 to the minus third meters. And you can get the electric field that goes through the stem of the leaf, causing this action to happen. Okay, let's look at the next one. Okay, so to what potential, or in other words, what voltage should a 3 microfarad, okay, so when you see that, you know that's the capacitance. 3 times 10 to the minus 6 farads. So what voltage should we have if we want to store 4 joules of energy? So that's the energy in the capacitor. So I don't remember the formula off the top of my head. Let me use this review button here and see what this looks like. Okay, it's taking a minute to open. It's just, if you think about it, you don't have to find your book, look through your book. This is right here for us. Hopefully this looks familiar to you. Energy 1/2 Q times delta V. Okay, that's good, but we don't have the amount of charge. We could figure out the amount of charge if we wanted to, maybe. 1/2 Q squared over C. We want it to involve C and delta V. So let's look at this part of it, actually. Second part here. That's not working like I wanted it to. Anyway, the energy on the capacitor, 1/2 C delta V squared. So we have the energy that's given in the problem. We have the C given in the problem. We just have to figure out how much delta V is. All right, let's take a look at that. Let's go back to the piece of paper. So again, how much voltage do you need for a 3 microfarad capacitor if you're going to store 4 joules of energy? So the energy in a capacitor in terms of C and delta V, that's what I just looked up. Why did I use this one? Well, it's because I'm given this, and I'm looking for this one. Okay, so multiply both sides by 2, divide by the capacitance, that's delta V squared. Take the square root of both sides. SI units, we're good to go. We can figure out the voltage. Okay, that was the final